Hi everyone, my name is Antonov Artem. I graduate student of Penza State University of Architecture and Construction, and I'm glad to present to you my work, Approach for finding amplitudes of the transmitted diffraction orders in the framework of radius-scope wave analysis. A radius-scope wave analysis is the method for finding diffraction efficiency of diffractive optic elements if these elements are periodic in two directions. This method is based on transformation of Maxwell equations using the assumption that electromagnetic field is a superposition of plane waves of various amplitudes. In the original work, Moharam described the method for finding only reflected orders or both reflected and transmitted orders. And he did not describe the method for finding only transmitted orders. In this method, microstructure is divided into a number of layers. Each layer is uniform in thickness direction. By the Floquet theorem, radiation is split into orders. These orders either reflect from microstructure or transmit through it. In this slide, you can see the matrix equations of boundary condition. The second equation applied to all layers. R and T are the column matrices of amplitudes, reflected and transmitted. C's are the matrices of unknown constants. Each layer has its own matrices. The key here matrices are Q and Y. They include Kx and Ky diagonal matrices of the components of wave vectors of all orders in the layer. E and M are the matrices of Fourier coefficients of the row expansion of the permeability of the layer. A and B are the matrices near amplitudes. Matrix I and C include column matrix delta. Elements of this matrix is Kronecker deltas. And all elements equal to 0 except the case when I and L equal to 0. Consider the first equation of the system. Rename I and C, A and R to phi 0, F G 0 and C minus 0. Transfer C minus 1, F G 0 and C minus 0 into our sides. And according to the rules of linear algebra, we get following equation. Multiply both sides of this equation by inverse of matrix near C's column. We get it. Rename again. We need only upper half of these matrices. Only C1 plus. Substitute it on left sides of second equation for n equal to 2. Rename again and we get this equation. This equation repeat on form second equation of this slide. Repeat this operation for all layers and we reached last equation of the system. We get the auxiliary matrices phi G, AB, alpha, beta and phi from the similar matrices for previous layers. Solve this matrix equation and we get transmitted amplitudes, column T. In this slide we can see one of the possible algorithms for implementing of this approach. I use a loop for and from 1 to uppercase N, and I use the part operator of Wolfram Mathematica for separate upper half of the matrices. This algorithm was tested by comparing with our approach of the enhanced transmitter matrix and scattering matrix approach. As we see, for all the values of the considered diffraction orders, the results of all algorithms coincide. In conclusion, I can say the method is developed for finding amplitudes of exclusively transmitted orders. This method saves RAM because it captures fewer elements. The results obtained using this method coincide with the results of our approaches. The described approach is suitable for tasks not related to checking the energy balance. Thank you for watching.